Hi, and welcome back to the Low Level Devil channel's Raspberry Pi Bare Metal series. In this video I'm going to show you how to use the Raspberry Pi firmware's Mailbox interface to communicate between ARM and the VideoCore GPU. This is not a very well documented API. There is some sparse documentation in the Raspberry Pi GitHub repository, but it's still very little. You can also download the 4.0 version of the Linux kernel to find some code that actually uses this API. The newer versions of the kernel have replaced the Mailbox API with some other methods. There's still some code in there, but I'd suggest using 4.9 as a reference if you want to get deeper into how the Mailbox API actually works. So let's get started. First, I'm going to show you where some of the documentation is here in the Raspberry Pi firmware wiki. So you find that on their GitHub page in the wiki section. So there's some information here. You'll see that, noticing here that the VideoCore is closed source. So there's not code in here, but there's a little bit of documentation. And this mailbox section is what we actually want. You'll see that's how you communicate with the GPU. So clicking this link, we kind of get a list of the different mailboxes and how they're used. So you can read through this. Some of the stuff's documented, like that one isn't. The frame buffer is somewhat documented. There's a little bit of information in that link, but not very much, honestly. Property tags section is probably where you get the most, but you notice this page is really short, so there's not too much. So let's click property tags. This has some decent information on how you create a mailbox message, the order that it needs to be in, the buffer contents when sending a message, and what the request and response should look like. So different values for like a success request and an error request. And then we have a tag format that has a tag identifier, the buffer size in bytes, and then some data containing the different codes used. And then a set of tags, this ARM to VC tags, so like getting the firmware revision, see some other stuff here, getting the ARM memory, the VC memory, the VideoCore memory. There's lots of different tags and stuff you can send for requests. Here's one to get clocks, so they'll get some data about the clocks. And also this link down here. So see here, this gives some information on accessing mailboxes, how you actually need to set up these requests, and some of the information about it. A little bit of a sample code on how you would do something like that. So that's kind of where this came from, and from some other open source projects as well, just researching how they did it, such as the Circle Raspberry Pi. So what I'm going to do is go in my kernel code here, get rid of all this LED stuff, so that this is going to start our mailbox section. And in order to start a mailbox, first I'm going to add a header file. And I'm not going to go into detail, so this is mailbox.h. I'm not going to go into detail too much on where and how I got all this data, because since it's mostly undocumented, it really took a long time to find all this data. Normally, if there's data available in a data sheet somewhere, I'll show you exactly where to find it and how to get it. But since this is so unwell documented, I'm not going to bother. So first I'm starting here with this mailbox tag as a structure. Each tag has an ID, and then it has a buffer size and a value size, or value length I'm going to call it. Okay, so now next I'm going to have another structure here, mailbox command. I'm not sure I'm actually going to use this, but this is one way to do it. So I can say command would have a size and a void pointer for the tag information, and we'll get more at that later. It would be referencing one of these tag objects. I'm not sure I'm going to use that, but for now I'm just going to put that there. There's going to be some other types of structures that we'll need. So let's go next on to this one. Will be the Mailbox Generic. What do I want to call it? Yeah, this will just be like kind of a generic command. I don't know if we want to call it tag generic or just generic. So that's going to contain a tag. So yeah, I think we'll get rid of that tag. We'll just call it Mailbox Generic. So inside of this structure, it's going to have a mailbox tag at the very top. So that's going to be our tag. And then it's got, this is a generic one. It usually has an ID and a value. So the input is kind of the ID and the output is kind of the value. Sometimes output is the value is input and output, but that's just a generic mailbox tag, I guess you'd call it. So I'm going to create a couple more here. Actually, this one could be used as a generic one as well, but since I know the name of the field, if we want to check the mailbox state of a power domain. So again, that could really just use Mailbox Generic as well, but I'll create a specialized one for it. Not all of them are only going to have that input and output as U32. Some of them will have many other fields, especially when you get into the frame buffer. So for this next one is another one that could have been generic. I'll just ID and rate. This is going to be for checking the clock rate. So if you want to get the clock rate of your UART clock or your core clock, and create an enumeration for the different types of clocks. So let's see, we have clock type as CT underscore, I'll make it uppercase, CT underscore EMMC is the value 1, UART is value 2, then the ARM is value 3, and then the core is value 4. So that'll be your core clock. So I'll call that enum clock type. Okay, so I think those are the basic structures we're going to start with. Next, I want to actually take some specific defines. So these power domain defines are the mailbox power IDs. So there's 22 of them, or 23 of them actually, and I can show you where you find that in the Raspberry Pi Linux firmware.h, and that's in the RPi 49Y stable version. So if you actually look down here, it's not this file, it's a different file. I can do a quick search on that. If I click this right. Alright, so I do a search, and yeah, here we go. So Raspberry Pi power.h. So I just copied those straight from there, and then there's the count, so there's 23 of them. Maybe I'll take that as well. Put this down here. So each of those are the different values you'd pass in for the ID when you're checking the status of a power domain. Sometimes you need to power on certain domains, as they call them, or power them off. So now I'm going to go back here. There's also in the firmware, there's a section for this is the property status. So you got a request value, then a success and error response. And then here's that tag header. This is what they're calling it. Notice the buffer size and the request response size. That kind of maps straight back to this generic one the mailbox tag one that we created, the ID, the buffer size, and value length. Okay, so then down here we have the different property tags. So that corresponds to the actual tag value. So these are kind of the different commands that you can send in through the Mailbox API to set up frame buffers and things like that. I'm just going to copy and paste that down here too. So yeah, looking through here, there's different commands you can do to allocate a frame buffer, blank one, get the pixel order. Let's see, you can release a frame buffer, and set the palette. So all kind of operations you can do on a frame buffer. That's how you actually use the video state. And here's some power. Here's the get power state. That's how we would do one of these power commands. But actually the newer version is this get domain state actually. So we'd use get and set domain state. And there's the set clock rate, so you can change clock rates, get clock rates. Right now we're just going to implement the getting the clock rates just as a starting point. And actually I think I'm going to take this other section up here. I'll take this as well so we can use those. I think that's everything we'll need in the header. And so now let's move on and create a mailbox.c. So we're going to include the mailbox.h. And there's a couple more headers, I think. So we'll include the peripherals base.h. Include printf if we want to print any error statuses and stuff. Is that it? I think you got also we need to include mem.h, which is something we need to create. In our current code base we don't have any kind of mem copy function, so let's go ahead and create a simple one. So to start with, I'll just do the pragma once in our header there, comma.h. And so it returns void pointer, takes a destination and a const source and a number of bytes. So let me create a mem.c and we'll put the simple implementation for it there. So we'll include mem.h, paste that in there. So we'll call this a really simple implementation. If you actually look up the source code for memcopy, it's pretty complex. So this simple implementation, we're just going to take two byte pointers, convert those void pointers to byte pointers so we can just iterate through each byte from 0 to n, and we're going to set b-dest I equals source I and return dest. It returns the destination. And I got something wrong here. Put a b source. There we go. Okay, now that we're past that, now we'll go on to the implementation of the Mailbox API. So to start with, we're going to need to be able to write to a mailbox, but actually we'll create some structures to create first. So one of them is the mailbox registers, and this is what we're going to read and write from. So the first register is a read register, then there's 5 reserved ones, a status register, a config register, and a write register. And we'll create a function a helper function here to just automatically return our mailbox regs from the address pointer. It's at pbase plus 0xb880. Okay, so next we move on to creating a different struct for handing our property data. So we'll call this the property buffer. So property buffer is going to have a size, then it's going to have a code, and then tags. So this will be an array of tags, and I'm going to map it to a U32 property data array. So I'm creating this here specifically because we need to use this attribute aligned 16, because it has to be 16-bit aligned according to the specifications that I've been able to find on these mailbox requests. So now that we have that, now we can start implementing the mailbox write function. So it's going to take a channel and then data to write. So the first thing we do is we need to loop while the status register has the mail full flag set. And all we're going to do is just loop indefinitely while that's set. And we don't have mail full yet. Let me find that. Yeah, I'll actually define this as mail full is 0x8000, and the mail empty is 0x, let me put a space there to line this up, 0x4 with a bunch of zeros. Alright, so that's what we need to do there. So now after we know that it's looping while it's full, then we're able to write. So what we're going to do is take the data, the full data section except the last half byte, and then we're going to OR that with the channel, but just the last half byte of that, so that the channel is the last half byte of the data that gets written. So that's the data section and that's the channel. Okay, so now let's move on and we'll do the static int mailbox, or sorry, static U32 mailbox read, because we're going to actually read data from a channel. So this is going to be a blocking request. So while true, it's going to check the status. If the mailbox is empty, then it's just going to do nothing, because there's nothing to read. Otherwise, it's going to grab some data. So calling read, and remember the bottom half byte of that is the channel. So we're going to mask that to get the channel. And if the channel on that read is the channel that we want, that we're trying to read from, then we're going to return the data. But again, only those top bits. Okay, and there's nothing to return here. I guess this is just going to block indefinitely until we find data on that channel. So yeah, and then it's going to return it masked with the data section. Alright, so now we can move on and we'll have a function called Mailbox Process. This is going to process a mailbox tag. So it's going to take the tag and the tag size. So the buffer size is going to be the tag size plus 8 plus 4. And that 8 and 4, trying to remember where that comes from. Yeah, oh, let me change that. That should be size. I believe that comes from down up here. So the ID and the buffer size and the value length. So that's, yeah, I think that was when I was going to use command for maybe the void pointer plus that size. But anyway, we can say that's 12, because of course 8 plus 4 is 12. Alright, so we have the buffer size. Now we need to memcopy the property data plus 2, because we don't want to start at the very beginning. We need to start at byte number 2 or the word number 2. You can also write this as and property data at index 2. So either way will work. So then we want to copy to the tag, or from the, I'm going to copy the data from the tag to the property data for tag size. And yeah, so here's actually our size, code, and then the tags. That's why we're saying, because we're mapping this to the property data section, so that's why we're starting at the second one, because size and code are passed over, and we're copying the tag data to the tags section. Hopefully that makes sense to you. So now we're going to create a property buffer variable in which we're just casting that property data to the property buffer. Alrighty. And now we want to set its size. So the size is going to be the buffer size, and the code is going to be, what that request. Let's see. Yeah, RPi firmware status request. So that's the code that we're going to use for sending a mailbox firmware request. Alright, so now what we need to do is set the property data. Now we want to get the tag size plus 12. Remember that 12 that we added. Now we're going to divide by 4 because this is a U32. That's a U32 array, so we're dividing that byte size by 4 and subtract 1. It's a little complicated, I know, but the very last byte needs to be this property end value. So we have all the data in that property buffer, and then it knows that it terminates when it reads that property end value, which is 0. Okay, so that's how it knows when there's no more property tags for it to read, by finding that property end tag. So now we can run Mailbox Write, and this is going to, we'll say mail tags, which that's not defined yet. I'll have to define that. So mail tags, I want to pass property data. That's the data we want to write to the channel mail tags. And that's a U30. We need to cast that as a void pointer to U32. Okay, now I'm just going to go up here and paste these in. This is just some defines for the different channels. I'll put it right down here. So you have the mailbox power channel, the frame buffer channel. If you remember that one document, it showed those different channels, and the tags one is the one that we're really going to care about, because that's where we're sending these tags to communicate from ARM to VC. So armed VC. So now that that's okay, so we're doing mailbox write, and every command is a mailbox write and a mailbox read. So this one, it actually doesn't return anything. I should just make that a void. Yeah, I'll make that a void. So for mailbox read, we can just do U32, and we'll call it result, I suppose. So the result is going to be mailbox read. And mailbox tags, so that's what we need to read from. And let's see. So now that we have that data, we need to copy the property data +2 again at tag size into the tags, because when we want to give it back to the calling structure. So you pass in that tag, then you write it, and then you read it and then copy it back into that tag structure from the property data. Hopefully you're following that. And looks like there's no chance of failure here, so just always return true. You can probably end up making this a void, assuming it's always going to return true. I don't like that idea though. So next we'll have a Mailbox Generic command, which will take in tag ID, an ID, and a pointer to a value so that we can use it for output. So if you remember, we had that Mailbox Generic structure. This is going to be a simple way to call that Mailbox Generic structure. So we'll call this Mailbox Generic MBX. We'll say tag.id equals tag ID dot tag dot buffer size, or actually value length we set to 0, because that will actually come back for us when it's returned. So now tag buffer size is equal to size of our mailbox generic structure minus the size of the tags, because the buffer is really only the data after the tag. So then we'll say ID equals ID and value equals dereference the value. So now if not mailbox process, let's see, and then we'll use the tag. Now we need to cast this mailbox tag. Remember the very first item in this mailbox generic is the tag, so it's safe to cast this to a mailbox tag. And size of MBX. I think we're missing a, there you go. Okay, so now we'll printf failed to process, and then %x, and we'll put in the tag ID. And we can just return false. And then finally, after we know that it succeeded, we can just dereference value equals mbx.value. And we can just return true. Okay. So that's how we'll invoke a generic command. We can do a more specialized one as well. Maybe we'll add one for the clock interface. Yeah, so let's add one for the mailbox clock. So to start there, we're going to create a new function down here. This one will just return the value, so U32 mailbox clock rate will We'll take in a clock type, and this is going to work very similar to the Mailbox Generic. So this is going to be Mailbox Clock. Yeah, just Mailbox Clock, and we'll just call that C, I guess. That's probably fine. So we need to set the tag ID, and this one is specific to RPi firmware get clock rate. Notice there's a min and a max as well, so you can get the minimum rate and the maximum rate. So we'll set the value length to 0 again. The buffer size will be size of C. We can just use C minus size of C dot tag. And then we'll say C dot ID is the clock type. And we don't need to set the value because that's an output parameter for this specific tag. And let's just invoke Mailbox Process. We know it doesn't fail, so we'll just invoke it like this. So again, cast it to a mailbox tag pointer, and C, size of C, and we'll return C dot rate. So that's going to give us the clock rate for that clock type. Okay, so that's a simpler API than the generic one, since it's specialized to the clock types. And you could implement a max and a min as well. For now, I'm just going to keep this simple as one small one. Let's create another one. We'll call it bool mailbox power check. So if we want to check the power of a certain power domain, the bool will be on or off. So we'll say mailbox power. We'll just call this P. We'll kind of do the same thing. I'm just going to be lazy and copy and paste here. Hope I don't mess anything up. So P, P, P. Change that to P, this to P, and that to P. And type there, and then this will change. So this will be RPi firmware get domain state. Okay. And on this one we actually do have to set the value, the state, as ~0, because we need to check check against the value. At least that's what the Raspberry Pi Linux code does. There's no documentation on that it must do this, but if that's what they're doing in the Linux kernel, then that's what I'll do. So again, mailbox process, pass that in, size of P. And now for here, we're going to return. So if p.state first bit is set, then we know that it is on. But also, we need to check that p.state is not equal to that ~0. So the inverted 0. So then, because otherwise that means it failed apparently. So I think that's all the code for the mailbox.c. So let's go into the kernel and start working on calling these APIs. Alright, so now back in this section underneath the spy init, I'll just start by writing some, let's see, we'll just say this is the mailbox section. And let's see, I think I'll print out some of the different clock values. So we'll say the core clock, and we'll call mailbox clock rate. And it looks like I didn't put that in the header. I'm going to have to add that. Alright, mailbox clock rate. There's probably a few things I need to add to this header. I want the generic one for sure. Oops. Alright, so I'll just copy the mailbox generic command and I'll put that in mailbox.h as well. Maybe that's enough for now. Yeah, because I don't need process, read or write. Don't need any of those in there. Yeah, that should be good. Let me save that and go to the kernel. Need to include that header as well. We'll say mailbox.h. So mailbox clock rate, and it'll be CT core. Okay. Yep, that's all I need. So I'll print each of these four. So we have the core, the EMMC, we have the UART, and the ARM. So CT-EMMC, CT-UART, and CT-ARM. Yeah. Okay, so let's also do these power domains. Let's see, the first three power domains are the I2C0, I2C1, and 2. So let's check the state of those three. So I'll say the I2C power state. So I'll go from 0 to 2. And let's see, we'll print F. I'm going to print the value returned. Mailbox power. I think I need to add that to my header file as well. So let's go back to the mailbox.c at the bottom. Yeah, power check. Okay. Paste that here. And let's see, power check. We're going to check the power for given type. Actually, we don't need that to be in an if statement. Let's just say, bool on equals mailbox power check, and pass in I as the parameter. Now we can just print out, we'll say power domain status for %d equals %d. So the first one will be I, and then the on status. So that'll tell us those first three what their power domain status is. I should probably show how to use generic as well. So let's do a simple one for that. Let's get the max temperature. And we'll just call mailbox generic command. It's going to be rpi firmware get max temperature. There we go. And 0 for the ID. And address of max temp for the output. So that'll give us the maximum temperature inside that variable. And we'll in this while loop, then we can check what the current temperature is. So we'll do that inside here. Now we're actually doing something at the end. So we'll call this cur temp. We'll just take this same thing remove max from here because we're just going to call get temperature and cur temp. Then we'll print out what the current temperature of the CPU is. So max %d, so we'll say cur temp and max temp. Oh, and we want to divide by 1,000 because the value it returns is actually higher value. So dividing by 1,000 will give us the actual temperature. That I just saw in the Linux code as well. It was returning high values, so I looked it up and they're dividing by 1,000. So then we'll just sleep for a second. So every second we're going to check the current temperature. So now let's just go ahead. I'm going to put the card in here. I need to mount it first. Let's see. Mount it. And now we can go ahead and build. Make clean. Oops, and make. Okay, now it built successfully. So I'm going to take the card out, put it in the Raspberry Pi 4. And we need to run the screen command to check the output. Alright, it's starting up. And you can see there's our different mailbox clock values. You see the power domain status for 0, 1, and 2 as well. So these are our different clock values. Power domain status 0, 1, and 2 is 0, 1, 0. So this I2C1 is on, but 0 and 2 are off. And you can see the temperature currently started at 32, now it's at 36. I'll leave that running as we do some changes here. So I'm going to copy and paste this loop a couple times. Let's actually turn those on. So I'll do a timer sleep, say 2 seconds maybe. So, and then a timer sleep for another 2 seconds, and just 1 second, just so we can see it as it's going on. So this will say set power domain status for %d to %d. We don't want to do power check anymore. We can do this the generic thing. If you remember, we had the generic command, and there was a set power domain state as well. So let's call this generic. And we'll create a U32 on equals 0. We'll say rpi firmware set, and I think it's domain. Yep, set domain state. And we want to put I there because we want to set the state for that specific one, and we want to set it to on, which is 1. Get rid of this. So essentially we're going to check the statuses, set the statuses to 1 for all 3, and then check the statuses again to make sure that the actual values got set. So yeah, this will be the check, this will be the set, and then this will be the check to make sure the set completed. So let's go ahead and run that. I take the card out. I need to remount again. Actually, look, you can see this is still running. Yeah, it's currently at 44 Celsius. While I'm waiting for that card to load up, just watch it. It's changing 44, 45. I actually put a little piece of ice on it. I have a whole piece of ice in my drink here. See, look at drop. 30 C, 20 C, 26, 30, 31. I just touched it with a little tiny piece of ice from my glass. You can see the temperature dropped significantly after that. So that's pretty neat. Okay, so let's go back here. I don't suggest doing that because you could probably damage your Raspberry Pi if you get water on it. But I was pretty careful. So let me go ahead and make that again. Alright, and I'll take the card out, put it back in the Pi. So let's take a look and see what happens when we run this. So I'm going to unplug it, plug it back in. Alright, it's starting up. There's our statuses, 0, 1, and 0. Setting them all to 1, get them again, and now they're all 1, so they're all set on. So we did a get, a put, and then a get again. So I think that's probably a good stopping point for this video. I think in the next video I want to start showing how to do the frame buffer stuff. That's how we'll be able to actually output to HDMI. So it's the same way that Linux used to use the frame buffer API for displaying to HDMI output. That gets pretty complicated, so might be a long video as well. So I hope you really learned something from this. This is a kind of useful API, especially if you're doing bare metal stuff. So if you did learn something from it, again, like, share, comment, subscribe, and all that. And thanks for watching.